Okay, let's talk about a convergence sequence now. Here's the definition of convergence sequences. We call the limit of xn as n goes to infinity equals to L if there corresponds to each positive epsilon a real number r such that this distance is always bounded by epsilon for all n values greater than r. You can think about some examples. Let's say the first example, limit n goes to infinity for n plus 1 over n is equal to 1. Because of this quantity is going to be true. So you can think about this term here. So this is n plus 1 over n minus 1, but this is same thing as absolute value of 1 over n, which is actually 1 over n. And remember that we want to bound this by epsilon, but this is going to be true whenever we have n greater than 1 over epsilon. And you can think about other examples like the exponential e. This is the limit of 1 plus 1 over n to the power n as n goes to infinity. So you can actually compute the elements of this sequence also numerically. So let's do a very quick plot in MATLAB to see the convergence behavior of this function. Remember, we can use the fplot function. We can define a function with respect to x. And what we are trying to plot is 1 plus, let's say, 1 over x to the power. Again, I'm using the vector dots notation to vectorize my function definition. So this is going to be x. And suppose that I want to do this from 2 to 100. So you can see this is the plot. And it indeed converges to the 2.718 something, this quantity. So that shows that the convergence is actually quite rapid. Another thing before we conclude this part is the order of convergence. So if we have sequences xn and alpha n be two different sequences, basically we write xn has big O of alpha n if there are constants c and n naught and 0, such that xn, this is our first sequence, can always be bounded by the second sequence times a arbitrarily large constant c when n is greater than or equal to this n0. So in other words, for all the n values, that is after a certain value n0, we can always bound the sequence xn by the other sequence alpha n. And there is also the little o notation, okay, which we use in this line here. Basically, if limit of xn divided by alpha n goes to 0 for n goes to infinity. You can think about different examples to understand this better. For example, n plus 1 divided by n squared. This is going to be big O of 1 over n because I can always find an arbitrarily large constant c to bound this sequence with the second sequence 1 over n. Okay? And think about another example, which is 1 over n times ln of n. In this case, this can be written as small o 1 over n, because if we take the ratio of these two and take the limit, we know that 1 over n divided by, this 1 over n ln divided by 1 over n, the limit will go to 0. So that's true. So this can be written as a small o. And another example, 1 over n, this can be written as small o 1 over ln n, right? Because if we take the, again, ratio and take the limit, this goes to 0. Another example, if you have 5 over n plus e to the power minus n, now let's think about big O notation. So if this is like the error of our, let's say, numerical scheme, actually you can notice that this converges quite fast, faster than this term, right? This converges to 0. It becomes much smaller for larger n than this term. So in order to bound this whole expression, basically we can only use 1 over n because this guy will be converging slower, and we need to make sure we can bound it. So this will be a big O 1 over n. The last example here, e to the power minus n, we can write this as small o 1 over n squared, because if we take the ratio, remember, by e to the power n divided by 1 over n squared. So let's write it here. So for this guy here, basically the limit n goes to infinity for e to the power minus n divided by 1 over n squared. This is 0, so that means we can write little o 1 over n squared. So this is how we think about the big O and small o notation, and you can try to write different examples, and this will help you to understand better.